All right, let's talk about a piece of tech that's quietly running a massive chunk of the internet you use every single day. It was born from a really simple but absolutely enormous question. In a world that's creating more data than we can even comprehend, how do you possibly manage that flood? Today, we're diving deep into Apache Kafka.
To really get a grip on the problem Kafka solves, let's just start with a single number, 7 trillion. That is the number of messages that LinkedIn, the company that originally built Kafka, processes every single day. It's a number so big it's hard to even picture, a constant, never-ending river of data.
And that number really sets up the core question, right? When you're operating at that kind of scale, things are going to break. Servers will fail. It's not a possibility, it's a guarantee. So how do you build a system that can take that just absolute fire hose of data, get it all organized, and deliver it where it needs to go without losing a single drop? That's the puzzle we're going to solve today. So here's our game plan. We'll kick things off by digging into the modern data problem itself. Then we'll uncover the big idea behind Kafka. After that, we'll get into the nuts and bolts of how it all works, how it manages to survive when things go wrong, and the kinds of guarantees it can make. And finally, we'll look at the legacy it's left behind.
Okay, so let's start with the problem. In today's world, sending a message isn't just about one person talking to another. A single event, a user updating their profile, a change in a stock price, a sensor reading from a factory floor. That one little piece of information often needs to be sent to dozens or even millions of different places all at once. It's broadcasting on a truly massive scale.
Let's make this super concrete. Let's say a huge celebrity posts a new photo on Instagram. That one single action, that one message, has to be delivered to millions of followers' feeds, and it has to happen pretty much instantly. How in the world do you build a system that can handle that kind of broadcast without just completely melting down or losing track of who's seen what? This one-to-many problem is a classic, and it's brutally difficult to solve at scale, and it's exactly what Kafka was designed for.
Okay, so how does Kafka solve this giant puzzle? Well, this is where it gets really interesting, because a lot of people think of Kafka as just a messaging system, but that's only half the story. It really has two distinct personalities, and it's this dual nature that makes it so powerful. On the one hand, you've got this super fast, high-throughput message queue. It's perfect for that Instagram problem we just talked about, blasting a single message out to a ton of different subscribers. But then there's this other side to it, and this is maybe even more powerful. Kafka is also a durable, ordered log of events. Think of it like a perfect, unchangeable history book of your entire system. If a user updates their profile picture, then changes their name, then their city, Kafka records those events in that exact order. The amazing part is, you can then have a totally new system replay that history from the very beginning to build up a perfect copy of the user's final state. It's a complete game changer.
And Kafka isn't some brand new, unproven thing. It was forged in the fires of LinkedIn way back in 2011 to deal with their insane data scale. Since then, it's become open source, and it's been battle-tested by literally thousands of companies, growing into what is now a fundamental pillar of modern data processing.
Okay, so we've got the what, but what about the how? How does it actually pull this off? You might be picturing something incredibly complex, but the core architecture is, believe it or not, beautifully simple. It all comes down to 3 key players that are intentionally kept separate.
First up, you've got your producers. These are any of your apps that create data. The Instagram app creating a post, a financial service noting a transaction. They produce a message and send it off to Kafka. Then in the middle, you have the heart of the system, the brokers. This is a cluster of servers whose whole job is to take those messages and store them safely. And finally, you have the consumers. These are the apps that actually need the data. They connect to the brokers and pull the messages when they're ready to process them. And this separation is the absolute key to its power. Producers have no idea who is consuming their data, and consumers have no idea who produced it. This decoupling makes the whole system unbelievably flexible and resilient.
So where does all this data go? Well, the brokers organize messages into categories, and we call those topics. You might have a topic for profile updates or user clicks, but here's the real magic for scalability. A single topic isn't just one big log. It's broken up into multiple, smaller, independent logs called partitions. This is huge because it means the data for one topic can be spread across many different servers, and more importantly, it allows multiple consumers to read from that topic all at the same time, in parallel.
And this brings us to one of Kafka's most important promises. Any messages that get sent to one specific partition are guaranteed to be stored in the exact order they arrived. And when a consumer reads from that partition, it gets them in that exact same order. So if you need things to happen sequentially, Kafka's got your back.
But, and this is a super important detail, that guarantee is only within a single partition. If you're looking at messages across different partitions for the same topic, there's no ordering guarantee between them. All right, let's switch gears and talk about something absolutely critical at this scale: failure. We've talked about the insane volume of data. When you're dealing with that, you have to assume things will break. You have to design for it from the ground up.
Exactly. When you're dealing with trillions of messages, servers going down isn't a maybe, it's a win. So what happens when that one broker holding your most critical data just disappears from the network? Does everything just grind to a halt? Do you lose that data forever? With Kafka, the answer is a resounding no, because the solution is baked right into its core design.
The answer, and it's a really elegant one, is replication. Kafka never stores a partition on just one server. Instead, it makes copies or replicas of that partition and stores them on other brokers in the cluster. For every single partition, one broker gets elected as the primary, or the leader. It's the one in charge, handling all the new messages for that partition. All the other brokers with a copy become replicas or followers, and their only job is to stay in sync by copying everything the leader does.
Okay, so now for the magic. What happens when that primary broker just vanishes? The whole system snaps into action automatically. A coordination service, usually something called ZooKeeper, notices the leader is gone and immediately kicks off an election. Now here's the critical part. Only the follower replicas that were perfectly up to date, the ones that were in sync, are allowed to become the new leader. One of them gets promoted, and within seconds, your producer applications can start sending messages again, completely unaware that anything ever went wrong. The system just heals itself.
So how does Kafka make sure nobody reads bad data during one of these failures? It uses this really smart idea called the high watermark. Think of it like a safety line. A message that's arrived at the leader isn't actually visible to any consumers until it has been successfully copied to all of the in-sync follower replicas. This is a powerful guarantee. It means a consumer can never, ever read a piece of data that might get lost if the leader fails before it was fully replicated. It's all about ensuring data consistency no matter what. Okay, so we've established Kafka is tough as nails. It's resilient. But what makes it so mind-blowingly fast? Well, it's not just one thing. It's a whole collection of clever engineering tricks and a really flexible approach to how it delivers data.
First off, there's batching. Instead of sending a zillion tiny messages across the network one by one, which is super inefficient, Kafka groups them together into larger batches. Producers do it, consumers do it, and it makes a huge difference. Second, it uses this awesome technique called zero copy. Normally, to send data from a file, you'd copy it from the disk into the application's memory, then copy it again to the network card's memory. Zero copy creates a direct shortcut, moving the data straight from the disk to the network. It's way faster and puts a lot less strain on the servers. Now, this is one of the coolest things about Kafka. It's not a one-size-fits-all system. You actually get to choose how reliable you need it to be. For things that aren't critical, like a simple notification, you can use at most once delivery. The message will be delivered once, or maybe not at all if something fails. For most things, like a password reset email, you'd use at least once. You're guaranteed to get it, but you might get a duplicate. And for the really critical stuff like financial transactions, Kafka can be configured for exactly once delivery, which is the holy grail, guaranteeing every message is processed one and only one time. So, we've talked about this data fire hose. How on earth do you actually process it all? You can't just have one application trying to drink from it. And the answer is consumer groups. You can launch multiple copies of your consumer application and tell them they all belong to the same group. Kafka then automatically divides up the partitions of a topic among them, making sure that any single partition is only being read by one consumer in that group. It's this beautiful built-in load balancing that lets you scale out your processing power just by adding more consumers to the group. All right, so when we put all of these pieces together, the decoupled design, the replication for fault tolerance, the incredible performance, you start to see why Kafka isn't just another tool. You can see why it's had such a profound and lasting impact on how we all build software. And this quote really says it all, doesn't it? When Kafka first came out, these ideas of immutable logs and event streaming were pretty revolutionary. But now, they're just the standard. They've become the default pattern for building modern, scalable, data-hungry applications. Kafka didn't just solve a problem, it fundamentally changed the way we think about data. So as we wrap this up, it kind of leaves you wondering, doesn't it? Kafka was born from the data challenges of the social media and web-scale era.
As we rocket into a future of generative AI, the Internet of Things, and data streams that are even more complex and massive, what are the new, unimaginable engineering problems that are just over the horizon? And what will be the next Kafka that rises to meet that challenge?